Title of the module: Operations on Ideals. We are familiar with various other operations like the operations on matrices, sets, etc. Let us now see operations on ideals. An ideal is a special subset of a ring. The concept of ideals were first proposed by Richard Dedekind in 1876. A generalization of the concept of ideal numbers was developed by Ernest Kummer. Later, the concept was expanded by David Hilbert and especially M.E. Noether. In previous modules, we have already seen about ideals briefly. So, let us now start with the definition of the product of an ideal. The definition of a product of an ideal with a set. Let J be an ideal of a ring R and let X be any subset of R. So, the product is defined by Jx is equal to the set of all summation over I is equal to 1 to n ai xi such that n is greater than or equal to 1 and ai belongs to J such that xi belongs to x for all I. Similarly, we can define the product of an ideal with finite family of sets. In this theorem, let us prove that the product of an ideal with a set is again an ideal. Theorem: let J be an ideal of R and let X be any subset of R. Then Jx is an ideal of R. Let us see the proof. We have Jx is equal to the set of all summation over I is equal to 1 to n ai xi such that n is greater than or equal to 1 and ai belongs to J, xi belongs to x for all I. Let summation I equal to 1 to n ai xi and summation I equal to 1 to n bi xi belong to Jx. Since J is an ideal, minus bi belongs to J. That is, summation I equal to 1 to n ai xi minus summation I equal to 1 to n bi xi is equal to summation I equal to 1 to n ai xi plus summation I equal to 1 to n minus of bi xi belongs to Jx. Also, R summation I equal to 1 to n ai xi equals summation I equal to 1 to n R ai xi belongs to Jx. Hence, Jx is an ideal. Note that the intersection of two ideals of J and K is same as set theoretic intersection of J and K. Now, let us verify whether the intersection of the family of ideals is again an ideal or not. Theorem: the intersection of any family Ji, I belongs to I, of ideals of a ring R is an ideal. The proof: let J be the intersection over I belongs to I Ji and let it be an intersection of any family Ji, I belongs to I of ideals where I is an indexing set, finite or otherwise. Let x comma y belong to J. We have to prove x minus y belongs to J and Rx belongs to J for any x comma y belong to J and R belongs to R. Since x comma y belongs to Ji for each I belongs to I, since each Ji is an ideal, x minus y belongs to Ji and Rx belongs to Ji. This implies x minus y belongs to J and Rx belongs to J. So, J is an ideal. The definition of an ideal generated by a set is: let R be a ring and consider X to be a subset of R. Then, the ideal generated by X denoted by X is equal to intersection over all J such that X subset of J and J is an ideal of R. For example, consider the ring of integers Z with usual addition and multiplication. Then, let X is equal to the ideal generated by 2. Then, 2 equals 2Z. Since we have the ideals of Z are NZ and the smallest ideal containing 2 is 2Z. The notion of ideals generated by subsets of a ring is analogous to that of subgroups generated by subsets of a group. Since the intersection of any non-empty collection of ideals of R is also an ideal and X is always contained in at least one ideal, namely R, we have the ideal generated by X is equal to the intersection of all ideals K such that K contains J. The definition of left ideals generated by a set. The left ideal generated by a set X is the intersection of all left ideals of R that contains X. Let us see a result. Let X be a subset of a ring R, then XR is a right ideal generated by X. The proof? It is following immediately from the definition that Rx is closed under addition and under left multiplication by any ring element. Since R has an identity, Rx contains X. Thus, Rx is a left ideal of R which contains X. Conversely, any left ideal which contains X must contain all finite sums of elements of the form Ra, where R belongs to R and an element A belongs to Xa, and so it must contain Rx. Thus, Rx is precisely the left ideal generated by X. We can also define the right ideal generated by X. Similarly, we can prove XR is the right ideal generated by X and RXR is the two-sided ideal generated by A. In particular, if R is commutative, then Rx equals XR equals RXR, which equals the ideal generated by X. Note that when R is a commutative ring and X belongs to R, the principal ideal which is generated by X is just the set of all R multiples of X. If R is not commutative, however, the set of all Ax b such that A, B belongs to R is not necessarily the two-sided ideal generated by A, since it need not be closed under addition in this case. The ideal generated by X is the ideal RXR, which consists of all finite sum of elements of the form the set of all Ax b such that A, B belongs to R. The formation of principal ideals in a commutative ring is a particularly simple way of creating ideals, similar to generating cyclic subgroups of a group. Notice that the element B belonging to R belongs to the ideal generated by X if and only if B is equal to Rx for some R belonging to R. That is, if and only if B is a multiple of X, or if we put it in another way, X divides B in R. Also, B belongs to the ideal generated by X if and only if the ideal generated by B is a subset of the ideal generated by X. Thus, containment relations between ideals, in particular between principal ideals, are seen to capture some of the arithmetic of general commutative rings. There are some examples of principal ideals. Example 1. The trivial ideal generated by 0 and the ideal R are both principal, since 0 is equal to the ideal generated by 0 and R is equal to the ideal generated by 1. In Z, we have Nz is equal to Zn is equal to the ideal generated by n, which is equal to the ideal generated by minus n for all integers n. Thus, our notation for R is consistent with the definition of Nz we have been using. These are all the ideals of Z, so every ideal of Z is principal. For positive integers n and m, Nz is a subset of Mz if and only if m divides n in Z, so the lattice of the ideals containing Nz is the same as the lattice of divisors of n. Furthermore, the ideal generated by two non-zero integers n and m is the principal ideal generated by their greatest common divisor, which is the ideal generated by m, n is equal to the ideal generated by GCD of m, n. The notation for the ideal generated by n, m as the greatest common divisor of n and m is thus consistent with the same notation for the ideal generated by n and m. In particular, n and m are relatively prime if and only if the ideal generated by n, m equals the ideal generated by 1. Next, we shall see a remark. The principal ideal generated by X in a ring R is the product of R and the ideal generated by X. The justification is that we have a principal ideal generated by X, which is Rx is equal to the set of all Ax such that A belongs to R. That is, Rx is equal to R of X. For example, we shall show that the ideal generated by 2 comma x, which is generated by 2 and x in Z of x, is not a principal ideal. Observe that the ideal generated by 2 comma x is equal to the set of all 2 into p of x plus x into q of x such that p of x comma q of x belongs to Z of x, and so this ideal consists precisely of the polynomials with integer coefficients whose constant term is even. In particular, this is a proper ideal. Assume by way of contradiction that the ideal generated by 2 comma x is equal to the ideal generated by p of x for some p of x belonging to Z of x. Since 2 belongs to the ideal generated by p of x, there must be some q of x such that 2 is equal to q of x times p of x. The degree of q of x, p of x equals the degree of q of x times degree of p of x. Hence, both q of x and p of x must be constant polynomials, which is integers. Since 2 is a prime number, q of x comma p of x belongs to plus or minus 1 comma plus or minus 2. If p of x were plus or minus 1, then every polynomial would be a multiple of p of x, which is contrary to the ideal generated by p of x being a proper ideal. So, the only possibility is p of x is equal to plus or minus 2. But now, x belongs to the ideal generated by p of x equals the ideal generated by 2, which equals the ideal generated by minus 2, and so x is equal to 2a of x for some polynomial a of x with integer coefficients, which is clearly impossible. This contradiction proves that the ideal generated by 2 comma x is not principal. Note that the symbol the ideal generated by x is ambiguous if the ring is not specified. The ideal generated by 2 in q of x is the entire ring, the ideal generated by 1, since it contains the element 1 by 2 times 2, which is equal to 1. Now, let us see some definitions here. First, the definition of the product of ideals is let J1, J2 so on up to Jk be the ideals of R. Then J1, J2 so on up to Jk is equal to the set generated by x1, x2 so on up to xk such that xj belongs to jj for all I comma j. That is equal to the set of all summation I equal to 1 to n xi1, xi2 so on up to xik such that n is greater than or equal to 1 and xij belongs to jj for all I comma j. Let us see the definition of the powers of ideals. It is a particular case of product of ideals, and it is defined as j power 0 is equal to r, j power 1 is equal to j, j power k is equal to j so on up to k times, it is multiplied k times, which is equal to the ideal generated by x1, x2 so on up to xk such that x1, x2 so on up to xk belongs to j. Let us see the definition of the sum of ideals. Let I and j be any ideals of R. Then the sum of ideals I and j, which is I plus j, is equal to the set of all x plus y such that x belongs to I and y belongs to j. It is the smallest ideal containing I and j. More generally, we may define the sum summation over I belongs to I, ji of any family of ideals ji of A. Its elements are all sums summation xi, where xi belongs to ji for all I belongs to I. It is the smallest ideal of j which contains all the ideals ji. Note that j plus y is the coset of j containing y, and j plus y is equal to j plus the ideal generated by y. Note that j plus y is the coset of j containing y, and j plus y is equal to j plus set y. The definition of the union of ideals. The union of ideals is the same as the union of sets. Note that the union of two ideals need not be an ideal. For example, consider the ring of integers z and j is equal to the ideal generated by 2 and k be the ideal generated by 3. Then j union k subset of z is not an ideal as it is already not a subgroup of the additive group of R, as can be seen by taking -2 belonging to j and 3 belongs to k and computing -2 plus 3 which equals 1, and this does not belong to j union k. Let us see a result. Let j and k be two ideals of a ring R. Then j plus k is equal to the ideal generated by j union k. Let us see the proof. Since j plus k contains j union k and j plus k is the smallest ideal containing j and k, we know already that the union of ideals will not be an ideal. But can we make them an ideal by constraining the ideals? Let us see this in the next theorem. Theorem: the union of two ideals is an ideal only if one of the ideals is contained within the other. Proof: let the ideal j and k be two ideals. Then j union k is an ideal only if for all x belongs to j and y belonging to k, x plus y belongs to j union k. If j is not a subset of k and k is not contained in j, then there is some x belonging to j and some x does not belong to k and y belonging to k and y which does not belong to j. That is, x plus y belongs to j or x plus y belongs to k. If x plus y belongs to j, then minus x plus y belongs to j, which implies that y belongs to j and hence it is a contradiction. Conversely, if j is a subset of k or k is a subset of j, then j union k is equal to k or j union k is equal to j, and hence it is an ideal. Note that the summation over I belongs to I, ji is equal to the ideal generated by the union over I belongs to I, ji. Here the example is R is equal to R of x1, x2 so on up to xn, and j is equal to the ideal generated by x1, x2 so on up to xn. Then j par m is a set of all polynomials with no terms of degree less than m. Next we shall see the definition of co-maximal. Two ideals j and k are said to be co-prime or co-maximal if and only if j plus k equals R. For example, in Z6, the ideal generated by 2 plus the ideal generated by 3 is equal to 0, 2, 4 plus 0, 3, and that gives you Z6. Therefore, the ideal generated by 2 and the ideal generated by 3 are co-maximal in Z6. Note that two ideals are co-prime if and only if there exists x belongs to j and y belongs to k such that x plus y equals 1. Until now, we had seen about the union of ideals. So, can you think what will be the intersection of ideals? Let us see this in the following result. If j and k are co-prime, then j intersection k equals jk. Proof: we have jk is a subset of j intersection k. If j plus k equals R, then j intersection k equals R j intersection k, which equals j plus k into j intersection k, which is a subset of jk. That is, j intersection k equals jk. The next theorem will show you the relationship between ideals and lattices. Theorem: the collection of all ideals of a ring forms a complete lattice with respect to inclusion. The proof: we have the ideal generated by x1, x2 so on up to xn is equal to the ideal generated by the set x1, x2 so on up to xn, and the ideal generated by phi or the empty set is equal to 0. Put I of R is equal to the set of all j such that j is an ideal of R. Here the inclusion in ideals has the following properties. Let I, j, k be a subset of R. Then Number 1, J is a subset of J for any ideal J of R and therefore reflexive property holds. For any I not equal to J, we have either I is a subset of J or J is a subset of I. Number 3, if I is a subset of J and J is a subset of K, then I is also a subset of K, therefore transitive property also holds. So, the collection of ideals with respect to inclusion is a partially ordered set. If S is a subset of I of R, then the greatest lower bound of S is the intersection of all ideals in S, that is GLB of S is equal to the intersection of all J such that J belongs to S, and the least upper bound of S is the ideal generated by the union of all ideals in S, that is LUB of S is equal to the ideal generated by the union of all J such that J belongs to S. So, I of R is a complete lattice. Next, we shall see some properties of operations on ideals. The three operations so far defined, namely sum, intersection, product, are all commutative and associative. Here, the result is let J and K be two ideals of ring R. Then we get the chain of inclusions as follows. JK is a subset of J intersection K, which in turn is a subset of J union K, that is a subset of J plus K. Proof: since J and K are ideals of R, JK is a subset of J and JK is a subset of K, that is JK is a subset of J intersection K. From set theoretic definitions, we have J intersection K is a subset of J union K. Finally, we can write J equals J plus 0 and K equals the ideal generated by 0 plus K. So, J and K are contained in J plus K. We have already seen that J plus K is the smallest ideal that contains J and K. Hence, J union K is a subset of J plus K. Now, let us see some examples. Example 1, put R is equal to Z, the set of all integers, J equals the ideal generated by M and K equals the ideal generated by N, where M and N belong to Z. JK then equals the ideal generated by Mn. J intersection K equals the ideal generated by the LCM of M comma N, and J union K equals NZ union MZ. J plus K equals the ideal generated by GCD of M comma N. Here, JK is a subset of J intersection K, which in turn is a subset of J union K, and that is a subset of J plus K. Let us consider the next example. Consider the ring Z8 with addition modulo 8 and multiplication modulo 8. Let J be the ideal generated by 2 and K be the ideal generated by 4. Then, JK equals the ideal generated by 0, J intersection K equals the ideal generated by 4, J union K equals the ideal generated by 2, and J plus K also equals the ideal generated by 2. Here, JK is a subset of J intersection K, which in turn is a subset of J union K, and that is equal to J plus K. Let us discuss some of the properties of ideals as a remark. Let J, K and L be ideals of the ring R. Then, number 1, J times K plus L equals JK plus JL. Number 2, J intersection K plus L contains J intersection K plus J intersection L. Number 3, K subset of J implies J intersection of K plus L, which equals J intersection K plus J intersection L. This is by the modular law. And number 4, J plus K times J intersection K is a subset of JK. One another example is, consider the set of integers Z to be equal to R and let A comma B comma C belong to Z. Then J is equal to A times Z, K equals B times Z and L equals C times Z. Then J intersection K plus L equals AZ intersection GCD of B comma C Z, which is equal to LCM of A comma GCD of B comma C Z, which is equal to GCD of LCM of A comma B comma LCM of A comma C times Z, which is equal to LCM of A comma B times Z plus LCM of A comma C times Z, which is nothing but J intersection K plus J intersection L. Further, J plus K times J intersection K is equal to AZ plus BZ times AZ intersection BZ, that is equal to GCD of A comma B times Z times LCM of A comma B times Z, which is equal to GCD of A comma B times LCM of A comma B times Z, which is equal to AB times Z, which can be written as AZ times BZ, and this is equal to JK. Let us see some definitions here. The definition of a direct product. Let R1, R2, so on up to Rn be rings. Their direct product R is equal to the product of all I equal to 1 to n Ri is a set of all sequences x is equal to x1, x2, so on up to xn with xi belonging to Ri for 1 less than or equal to I less than or equal to n and component wise addition and multiplication. And the definition of projections on the products of ideals. A is a commutative ring with identity element 1, 1, 1, so on. We have projections Pi from R to Ri defined by Pi of x is equal to xi. Finally, let us conclude this session with this remark. Let R be a ring and J1, J2, so on up to Jn be ideals of A. Define a homomorphism phi from R to the product of I equal to 1 to n R by Ji by the rule phi of x is equal to x plus J1, x plus J2, so on up to x plus Jn. Then number 1, if Ji comma Jj are co-prime whenever I not equals to j, then the product of all Ji equals intersection of all Ji. Number 2, phi is surjective if and only if Ji comma Jj are co-prime whenever I not equals to j. Number 3, phi is injective if and only if the intersection over all Ji equals the empty set. Dear learners, first we had seen the product of ideals and the set, then we discussed about right and left ideals, the union and intersection of ideals, the ideals generated by a subset, etc. Also, we had some of the properties of the ideals and we discussed them in detail. Finally, we saw about the homomorphism of ideals. We will meet you in the next section. Thank you.